So last time we started talking about graphs of circular trig functions. So 1, 5, this is just quickly go back and review what happens. Our objective is to graph y equal to sine of x or y equal to cosine of x and so on. We said one style that never fails but it's rather primitive is point plotting. Just sit down patiently, figure out your x and y's. So style 1 would be point plotting. So you make a table of x and y values, perhaps using your calculator, and every pair of numbers that you find here, you plot it and connect them to each other and hope for the best. Okay, so this is rather primitive, takes a lot of time. Sometimes we could take a leap of faith that might be incorrect and such. We said, okay, how about style number 2? Style number 2 using the unit circle. The idea is to be able to recreate the picture from scratch in a matter of few seconds and get going with whatever else you're supposed to do. Unit circle means a circle that has its radius is 1, so the radius is your yardstick. So we imagine this to be our unit circle situated in our coordinate plane. We said for any angle that is in standard position, so if you have angle theta, to figure out the sine of theta, we have to take the ratio of opposite to the hypotenuse. So this is my opposite. Hypotenuse is the radius, which is 1. This hypotenuse radius is equal to 1. So sine of theta becomes equal to the height of this green line. Sine of theta, if you want to have a visual impression of what your sine is supposed to be, you draw your unit circle. So the radius of this acts as your yardstick from here to here is 1. With respect to that yardstick, you measure your height, y. The length of that green line is exactly the sine that you're after. So instead of using the general formula we had before, which was the y divided by r, we are using something simpler because your r has become 1, and when you divide the number by 1, you just get that number. So the trick with the unit circle is that it simplifies your division. You don't have to actually carry out a division anymore because denominator is 1. You're just looking at the numerator alone. That gives you the answer. So when we want to graph y equal to sine of x, I have to graph these two entities with respect to each other. I have to graph this angle theta, however I decide to measure it, degrees or radians, versus this height, which is y. Here, let's go do, let's see if we can remember how to do it quickly. My angle, let's say we want to go in degrees. So if I want to go in a circle, perhaps my angle starts at 0 degrees and I turn around all the way to 360. So let's figure that situation. 360, I divide it to some famous milestones here. So I start at 0, say 90, 180, 270, 360. Now I ask myself, when I just get started, how tall is this green line? When my angle is 0, that's the section you have to visualize in your mind and quickly run that through that animation in your mind to be able to handle the situation. So when this angle is small, just try in your mind, try to imagine that this has been pushed all the way down to this point. What's going to happen to the length of y? What happens to it? It becomes becomes short, becomes 0. Is that right? Well, let me show it here. Okay, let's go to one of these applets, see what happens. So maybe that gives you a better impression. You're supposed to do this thing in your head. Okay, that is replay the same thing that you see here. Okay, and on this applet you can choose any of these 6 functions. Let's just choose sine. What can you do? Here's your angle, you can drag it. What is the angle? This red angle that you see here is your theta. That yellow line, the length of it is your sine. Here is giving you that sine in numbers, in 3 digits. So if I go all the way down here, what happens to this yellow line? It disappears. Is that right? Becomes tiny, becomes 0. As I come up here, this yellow line approaches what? 1. My angle has approached what number now? I'm almost at 90 degrees, or pi over 2 radians, however you want to think about it. Is that right? So again, this is what you play in your head. Say, okay, you see that tiny yellow thing that's almost 0. It is increasing. It comes all the way to its maximum, which is the radius of the circle has become 1. Now I start to descend. The angle is increasing. I'm between 90 and 180. At 180, what happens? At 180, here's the angle. When I come close to the angle, that's what happens to my sine. It comes close to 0. I become almost 180. Let's see if we can actually. It's 179, almost showing 0. You go to 3rd quadrant. What happens now? Your sine, again, is the length of this line, except that it has to be measured on this vertical axis. It's negative because we are going down now. So by the time I make it to 270, I have made to -1, and then I shrink back towards 0. Okay, so that is the picture you want to play in your head. Here's another way of looking at this. Here's a slider that you move instead of playing with the point over there. As I move here, x is measurement of my angle. You have to be kind of clear on as to what x is supposed to be in these pictures. So x is measuring my angle. I go ahead, for example, this is my 90 degrees almost. Sine of x is shown here. So what is it that we are drawing? On the horizontal, I am measuring my angle. Like, for example, my angle is 49 degrees. From here to here, supposed to be 49. My vertical is sine of x. Visually, what is that? Well, that's the length of this line. If you open this angle as much as you want, like 49 degrees, whatever this length is, that's what you're supposed to draw here. So on a horizontal, you put how much this angle is, this opening angle, you lay it down here, and this vertical is just a copy of the vertical here. It's color coordinated so that you see what's going on. So as you go around, you see that you get the sine curve. If I go on the negative side, I see a little bit of the other side as well. Okay, so that was sine. You can do the same thing with the tangent and cotangent. And again, the question is, to play this picture in your head. You should be able to do this thing. That is, visualize the situation that the angle is opening. Keep track of what size angle you have, and plot it against how tall this line is going to be. So as I keep moving, that line shrinks. The best way to track things for yourself is perhaps to figure out what happens at these 4 corners, multiples of 90 degrees, to make sure that you are not going wrong about your assumptions. Okay, so you have these two, and well, this is just the plain graph. Okay, so this is just showing the whole picture without animating how it comes about and such, so you can go ahead, just see the 6 pictures. And okay, coming back to doing the same thing ourselves. So you are visualizing this height versus the size of this angle. To aid yourself, perhaps you want to aim at some famous angle. So at 90 degrees, we know we're hitting 1. At 180, if I open my angle almost close to 180, that height becomes 0. At 270, that height has become -1. At 360, if I come back here, that height is again going back to 0. So the picture that I get is something like this wave. We also mentioned a few facts about this situation. We said there is a concept of a period that is the smallest distance, smallest positive distance you go before the picture repeats itself. This sometimes is referred to as one cycle. The first example of it might be referred to as the fundamental cycle, and then you work off of it. So that is the deal with the sine. Let's quickly figure out what the deal was with cosine. Y is equal to cosine of x. So we draw a unit circle. If it was some arbitrary circle, I have this angle theta, and at this point, I had my points with coordinates x and y and distance r. Cosine of theta would have been the ratio of, so this adjacent is x, opposite is y, hypotenuse is r. Cosine of theta would have been adjacent to hypotenuse. Now, if your circle is a unit circle, again, the insistence on unit circle is to make our life easy so that we can do visualization. We don't want to have one more thing to worry about here. We don't want to deal with the fraction. So we have taken radius to be 1. So cosine of theta becomes this adjacent length, that is this x here. To track it off of the moving point, I'll consider this distance. So while I am the idea is the following. So you open this angle, so the size of this angle has to be plotted against the length of this line. So if this is your theta, this is cosine of theta. So how do we do that? Again, the main issue is, can you do this thing in your mind's eye? Imagine this theta is 0. We just started. How long is this black line? Okay, so when I start here, the length of this line, you're going in this horizontal direction. The length of that line is 1. How high should I go before the length of that line becomes 0? What's the first point at which? So you're tracking this line in your head. And for each of these things, you have an angle that goes with it. So for this line, the angle is this one. For this line, the angle is this one, and so on. So as I come all the way up here where this line shrinks to 0, what is my angle? 90 degrees. So at 90 degrees, I have made it to 0. So this height is shrinking to 0. Then I go on the other side. On the other side, well, when I'm measuring on this side, what happens to this? Is it positive or negative when I'm on the left? All these horizontal lines, they are negative. That indicates that the graph of cosine is sinking below the x-axis. So this is 180. I draw a line the size of this little green mark. I open the angle some more. I draw a line like that. Open the angle some more. I draw a line like that, and so on I go. So that's from 90 to 180. The situation is like that. Then suppose I'm in the third quadrant. What happens? In the third quadrant, my angle is increasing from 180 to 270. So it is 180. This is 270. And these heights are still negative. They are starting at -1 and gradually shrinking towards 0. So if I plot those lines here, each of them for the angle they represent, they start at -1 at this corner and shrink towards 0. Then I go to the fourth quadrant. In the fourth quadrant, so I have this horizontal length is to the right. So what does that mean? That means it's positive. It starts at 0 here at 270 and marches toward 1. So I have this angle increasing toward 360. So here's my 360, and the heights are increasing, and then they make it all the way back to so this was 270 and this is 360. So this becomes the graph of cosine of theta. And of course you have to deal with this as a tile, that you can pick it up and place it next to itself and repeat your pictures as often as you wish. So if I want to shrink it, say this is 0 to 360 is one fundamental cycle. It kind of behaves like this. Then you can copy it next to itself as many times as you want. So that on 360, you go twice that will be 720. If you want to go one more round, well, be my guest, go one more round. So the third round of this thing, by then 3 times 360, or move 360 more, is 1080. If you want to back up, you can also so this is going to be minus 360. So these are all copies of the fundamental cycle. We've just put them all over the place, and that becomes graph of cosine. I should have written cosine of x. Okay, this is for sine and cosine. Now we have a next challenge in front of us, which is what's going to happen with tangent. That's going to be a little bit more sophisticated, because we want to graph tangent of x. The issue with tangent, well, what is tangent? Tangent is a ratio of, so if I have this angle theta, and these are my sides A, B, C, tangent of an angle is a ratio of opposite to adjacent. That's how we learned the very first lecture. Then we come and say, if you have an angle drawn in the coordinate plane, this is your angle theta. So consider this point with coordinates A and B. Then tangent of theta, instead of thinking about opposite to the adjacent, think about the y coordinate divided by the x coordinate. Why is that so good? Because if you are in the second quadrant, third quadrant, or fourth quadrant, you don't have a triangle to play with anymore, but you have your coordinates. You use that instead. Okay, what is so big deal about tangent that is different from sine and cosine? The big deal about it is that you are taking a ratio of opposite to the adjacent. That adjacent could be very small. Like you could have a picture like this. What kind of number are we going to get for tangent of an angle that's close to 90 degrees? So suppose I have an angle theta that is, say, 89 degrees. What kind of an answer do you expect we are going to get, say, if we are dealing with 89 degrees? Qualitatively speaking, what is happening here? Ratio of opposite to adjacent. What kind of numbers do we expect? We expect a large number. Is that right? Unlike sine and cosine, sine and cosine was a ratio of opposite or adjacent to the hypotenuse. These guys, these legs are always less than the hypotenuse. So when you take the ratio, your ratio is bounded to by 1. You never go above 1. You never come below -1. But with tangent, you don't have any limitation. You're taking ratio of these two. That ratio could turn out to be any number. Most problematic about the situation is, well, what if the denominator becomes 0? That is what we mentioned. You get so-called vertical asymptotes and such. Okay. Or large. Just a large number. Like you can use your calculator to figure out the tangent of. Let's go play with it if you wish. We can go ahead and just plug some. Okay, here's our calculator. I want to take a look at some angles. Let's say tangent of 89 degrees. Tangent of 89 degrees is 57. Large number, is that right? Like sine and cosine, everything was reasonable numbers like 0.5, 0.7, 0.9 or something. But all of a sudden we are dealing with large numbers. Let's see what happens if I come closer to 90 degrees, like here. Let's come closer. 89.9. What happens to my tangent? 572. What do you think? What's your guess if I put the next 9? 5,000. Next 9. 57. Essentially what happens is that that decimal point keeps marching toward the right. I come closer to 90 degrees. That guy keeps running without bounds. It's going to get, by now it's 5 billion and so on. More 9s you add, the further down this decimal point is going to go. So that is something that we need to live with. Now, I don't know if this calculator can handle 90 degrees. Let's see, what does it say? Okay. You have to be careful how to read this thing. What is E16? What does that mean? Your calculators typically show up with that kind of a symbol as well. What does that mean? It's an exponential notation. It means all of this number, 1.6, etc., times 10 to the power of 16. 10 to the power of 16 means 16 zeros in front of your number. That's essentially the largest number this calculator could show. So instead of saying infinity, it says, okay, this is the biggest I could give you. I give you that number. Some calculators might say error. Some other calculators might show NaN for not a number. Some calculators might say infinity. Depends on how much you paid, essentially, how smart they are in dealing with the situation. So we don't go right on the 90 degrees, but we said if you come close to it, the closer you come, the larger this number is going to be. Well, what is that going to do to our picture? Let's see. Now, dealing with these numbers is going to kind of sidetrack us into a lot of nitty-gritty stuff that doesn't really say much. We want to get the picture and get moving with doing other stuff. Let's see, how do we handle the situation? Again, we call the unit circle to come to our rescue so that we can undo this, the tedium of this division. The issue is that how do you deal with this division? And unit circle, what it does is that it takes that job off of your hand. However, you have to be careful. Let's draw a unit circle. So I draw a unit circle. I placed it in the By the way, this is different from the way the book presented. The book says essentially go figure it out and see that the picture is whatever it is. There isn't really much of a discussion there. So here we draw an auxiliary axis. From this point, the right point of the circle, I draw another axis here going up and as well as down. So it's the positive direction of this axis. Previously we had figured out cosine down here. Sine was measured off of this axis. This one we are going to call it tangent axis. Why so? Well, let's open an angle. Let's see what happens. Suppose I open an angle in the standard position here. So let's call this an angle theta. This angle theta, notice that I'm cutting through the circle and going all the way to this green axis. Let's name the three sides in this picture. Let's say A, B, and the C. So tangent of theta, according to the definition in this picture, is supposed to be what? Ratio of which two numbers? B over A. Now, what is the main claim to fame of the unit circle? When we keep insisting I have unit circle, it means what? One of these numbers is nailed down to be 1. Which one of them is it? C is from here to here. So again, question is which one? A. So the reason I drew this line at this place is to get the adjacent to be fixed to be 1. So what is so great about that? The great thing about it is that I'm lazy. I don't want to do this division. I want to just be able to look at it and say, okay, this is the tangent. I want to be done. I don't want to have one more thing to do. I don't want a project on my hands. Okay, you want a tangent. All you have to do is to look at this. No division to be done. It's right in front of your face. That is the tangent. That is, since you are dividing by 2, so if I draw a line, and this is my yardstick, and I'm asking what is the tangent of this angle, all I have to do is to measure this. For example, this looks like, with this being the unit, this looks like almost 2 or 1.8. Whatever this angle is, I can look at it and say right off the bat, its tangent is about 1.8. Now I draw a few angles, and you do the best you can do with your eye, eyeball it, and tell me what do you think the tangent is. So we have nothing in our hand. We just have our eye to work with. We just draw an angle, and you tell me tangent of those angles. So I draw this axis here. Okay, one by one. I start from here, and suppose I end up at this location. Question: what is your best guess for tangent of this angle? If you have done any carpentry, any wall working, any quilt making, if you have done anything with your hand, you should be able to say the answer. Tangent of this angle, I want to expect a number, an approximation for that number, and you are just eyeballing it. What is that? 0.5, because you say this is 1, this is my 1. Okay, by your eye you can tell this is my 1. This is almost halfway, or you could say a little bit higher. You could say 0.6. I wouldn't argue with that. So this looks like almost 0.5 or say 0.6 or whatever it is. This angle, whatever it is you drew, we are just doing visual. Whatever you drew here, its tangent almost 0.6, because this is 1, that's going to be 0.6. Now, if you haven't worked with a ruler or you haven't drawn a picture really, you will have a hard time here. But other than that, it should be straightforward. So let's go to this angle. Now, I made the angle is bigger. What's the tangent of that angle? Almost 2, because I'm almost here. So let's do one more round. So what's the tangent of that angle? 3. Now, suppose I keep going now. All of my how about this one? 6. Looks like 6. If I keep going, what happens to this angle and what happens to its tangent? If I keep inching up toward the vertical, what happens to this? Escapes to infinity, is that right? So your angle comes to 90 degrees, its tangent becomes infinity. So we can say as theta increases from 0 to 90 degrees, its tangent, or let's just say tangent of theta increases from 0 to infinity. Infinity we show by this symbol. Now let's go the other way. What if I had an angle like this? You remember when you're coming down this way, angle is considered to be negative, or if you wish, you could go all around and come back here. That is you get the same trig functions out of that. Either way, what is the tangent of that angle? If we said this is an axis here, this is a tangent axis. So if I go down, it means it has to be what type of a number? Negative number, so minus 0.5. What if my angle was like this? Almost looks like minus 1. I come down, it looks like minus 2, minus 3. So as this angle marches down toward minus 90 degrees, or if you wish, it could come from the other way. Let's take this negative direction. My angle is going from 0 to minus 90 degrees. What happens to its tangent? So say as theta decreases from 0 to minus 90 degrees, tangent of theta decreases from 0 to, what should I write for the number that shows up at the very bottom of this line? Minus 1, minus 2, minus 3, minus 4, and so on. All the way at the bottom is minus infinity. Now what we need to do is to capture this movement in our head as a animation and plot the whole thing on a graph. Let's just do it by hand once, and then we go look at those applets one more round. So suppose I want to graph y is equal to tangent of x. So okay, we saw that something is special about 90 and also minus 90 degrees. As the angle, let's redraw this unit circle for ourselves. It had a tangent axis here. You are opening your angle like this. So whatever this angle is, you are laying it down here. So that is your angle, and the length of this thing, whatever this happens to be, that is how high you go up here. So this is your tangent of theta. Okay, so this theta is however you measured your angle in degrees from here to here in blue. This black one is what you mean by tangent of theta. So if this blue angle is 0, what's my tangent? 0. Some famous cases, you know, for example, at 45 degrees, what's your tangent? So you have a little bit of a something to guide your hand. In between 0 and 90 degrees, you're supposed to pass through 1, wherever your 1 happens to be. Now, the issue is that as this blue angle marches toward 90 degrees, what happens to the length of this black line? It increases. So as we go close to 90 degrees, whatever it is, this line keeps escaping all the way to infinity. So the graph that we draw of the tangent is something like this. It keeps going up, escaping through all boundaries we might put for it. It just escapes right off. It goes toward plus infinity. As if there is a wall here, and as if, or a cliff, and some airplane come close to it, has to avoid it, has to go straight up. That cliff, or the face of that cliff, we refer to it as a vertical asymptote. So this is a vertical asymptote. Vertical asymptote indicates where you have divided by 0. In this case, when your angle was 90 degrees, when this x is 90 degrees, this thing escapes to infinity. We said the same thing happens at negative angles. As I march toward minus 90 degrees, this thing goes down. Now, if I want to graph them, let's go ahead and, for example, graph, see if this color works for us. If you have a negative angle, you are going down. So if I have, for example, minus 45 degrees, I'm supposed to go down here. If I have a bigger angle, this line gets to be bigger. So what does that do to my picture? That this bends down this way, and there is another vertical asymptote. So another vertical asymptote we are going to abbreviate to VA. The location of this other vertical asymptote is at minus 90 degrees. Now, we are running out of time. Let's see. This is from minus 90 degrees to 90 degrees. Suppose I keep marching from 90 to 180, and then from there I want to march to 270 and so on. What happens if my angle, let me erase this thing, or perhaps you can tell me first and then I erase it and do it again. Suppose, question? Suppose I am in the second quadrant. What kind of a tangent am I going to get? I draw my line. If I go in this direction, I'm not going to hit the tangent axis. I back up until I hit my tangent axis. Am I going to get a positive or negative quantity for the tangent of this angle? This is in second quadrant. Negative. So as soon as I pass the 90 degrees from like 89 to 91, this picture jumps from going from positive infinity, re-emerges at minus infinity. Okay, this was going up. As my angle was increasing, this thing kept going up and up. As soon as I passed that 90 degree angle, that intersection jumps all the way down here. This might remind you of some video games you guys used to play a few years ago, those Pac-Man, and the creature exits from that side, it re-emerges from this side. You remember that? Okay, this is the same thing. This goes to plus infinity, re-emerges from minus infinity, because at like 91 degrees, I am down here. As my angle increases toward 90 degrees, I march back toward 0. So this starts at minus infinity. At 180, makes it through 0. When I go to the third quadrant, it comes back to the positive territory, and by the time I make it to 270, it shows its asymptotic behavior again. So what we see in the tangent is that it has a cycle that is just this long. The cycle of it, or the period of it, is 180 degrees. Unlike sine and cosine that were 360. This is your tile. You take this is your tile. you put that tile next to itself, you get the second piece of this puzzle. So let me go ahead, clean the picture, and end the lecture. We are looking at tangent. For drawing the tangent, you mark your territory at multiples of 90. So this was 0, 90, minus 90. At these two, you draw your vertical asymptotes. Picture of tangent starts from the bottom of this, passes through origin, and goes up. Then you repeat this thing. Like from 90 to 270, you have another piece. At 180 is the midpoint, and this is the second piece of that puzzle. So this becomes a graph of y is equal to tangent of x. You want to read the text, you want to play with those links on the website, and you want to draw it yourself to make sure you understand what is going on. And then at the end, you want to memorize the pictures. Okay? So we'll talk about the other three functions in the next episode.